Cool. We are now live.
Cool.
Perfect. Well, maybe just like a couple quick things before we let Brendan get going. Rowan started a MailChimp mailing list, so you guys may have gotten an email last night with that, and so we're going to try that out and use that as a way to send out notices and things like that. So please stay signed up, and then if you are getting I think we can configure like what styles of emails you get and things like that as we maybe get more familiar with it.
Yeah, so if you do go to the MailChimp side of things, which is at the bottom of that email that I sent up, there's a couple of check boxes that you just check about like what in terms of like I want to hear weekly updates versus maybe something much less frequently when a paper is published or something like that. That will send the right email to you.
Yeah, so that'll be great. And one more quick notice with that is that Craig, his paper is coming out. When is that coming out, Dom? Do you know?
He said the next couple of days, I think. I'm not sure.
That's very exciting. That's awesome. So we got his example.
Dom, can you give a quick overview of what that paper does, actually?
Yeah.
It's just a gravity inversion over over an old volcano. They want to see the size of the chamber, so he used SimPEG to invert for the volume of the chamber. And Darcy, you guys remember Darcy from Banff is coming on Thursday, and he's gonna look if we can because he's working on the exact same property, so we'll see if we can use MT and gravity together. So that could be a nice follow-up paper. And please download and read the paper.
Yeah, and I think the cool part about the results in that paper are both hosted on the SimPEG site and completely reproducible on every commit, basically. They're tested, so that's kind of cool.
Very cool. Yeah, so with that, we will let Brendan take it away. So thank you very much, Brendan, for being willing to give us a talk. I'm sure you guys all know Brendan, but he is now at Western, and at Screenpoint.
Yes, both. Kind of
both. And so he's going to be telling us a bit about Parallel in Python. He's got lots of experience with the Zephyr project, which uses SimPEG a fair bit. And so with that,
and Lindsay, can you make sure to select Brendan on the?
Yeah, will do.
Cool. Perfect.
Perfect. Take it away.
Okay, thank you. Yeah, so Zephyr is this project that I worked on as a postdoc at Western, and in recent months I've been working at 3 Point Science, which is I think as a few people know, it's a pretty cool place. And so Zephyr is this project that was trying to, and it needs a bit of work, but still is trying to take the seismic full waveform inversion problem and do some of the same sorts of things that have been done with SimPEG. The big difference being that Zephyr had a little bit narrower focus in that it was meant to be competitive in a performance sense with, and also in terms of the feature set in some of the core features that we need for computation with this older Fortran code called full wave. And full wave is a product of probably, at this point, almost 30 years of work. There are commits in that code base, or at least comments in the files from about 1988. And so I've talked a bit about the challenges of getting those two to work together. But the big thing that is really interesting is that in a lot of cases, actually, doing a new rewrite from Python opens up a lot of possibilities, and the performance can be really comparable to what one can get with something like C or Fortran, with these traditionally, these languages that we tend to think of as fast. And I was trying to think of a good analogy for this, and I think a lot of people here, the people I know who are active in the SimPEG group already know this, but if there are people watching, they may not have had as much experience with this kind of idea, but it's kind of like to go out of the sphere. It's like maybe investing. So if you think about it, if you're trying to invest your money, unless you're really, really good at it, you're going to lose a lot of money if you try and hit the stock market. So what you do is you go to something like a mutual fund, right? Which is this way to say, there are smart people out there who already know how to do this, and I can take advantage of what they're doing and apply that to what I want to do with a lot less risk and using best practices. And I think that's really what the Python computational ecosystem is. To get the best performance out of codes that we're writing in C or Fortran, I think you need to be a computer scientist. And so, if you're trying to do something like geophysics, chances are you're either not getting the best performance or you're actually a computer scientist and you just don't realize it. And I think that one of the things that SimPEG is really good at is letting geophysicists do geophysics and also make use of computers in a really interesting way. And so Zephyr, in that sense, I think, tries to do some of the same things. Where it diverges, and now I'm going to share my screen. Is that coming through okay? So where it diverges is I think, in the details. If you look at the SimPEG project, it's built around the idea of having these composable pieces that let you symbolically express the mathematics of your problem and the physics of your problem. And I'm not anywhere near as familiar with this with these docs as the rest of you guys are. So, but the idea here is to be able to express things in a way it's very close to the mathematics. Zephyr, on the other hand, is really designed to take some existing algorithms that we already had and make them work in a new Python ecosystem. And so Zephyr, for the most part, solves this equation, which is a 2D acoustic Helmholtz equation, or one that's a little more complicated than this, that allows for density to be variable. And this is not that complicated a problem to solve compared to some of the the Maxwell's equation problems and so on that have a lot of different components. This is a scalar field, and so a lot of the subtlety comes in the fact that the grids that we're trying to solve these things on are in 2D sometimes quite big, and the size of the data that are going in are quite big. And so we're also trying to solve inversion problems. In that sense, it's a lot like SimPEG. We want to take data that we measure in the real world, and we have some concept of an Earth model, and we'd like to minimize things such that the data that we simulate in our Earth model look as close as possible to the data that we observe. So all of that is pretty similar. The big difference is that Zephyr, instead of implementing things in a symbolic way, actually just has a specific discretization that it implements. And so there's one here that's charmingly called Mini Zephyr, which is a 2D viscoacoustic frequency domain wave equation with variable density. And so this is all about constructing finite difference stars and so on. In a symbolic way, the code is gross, but the goal here was for this to be better than our existing Fortran code, and it's like way worse. I don't know if it's easy for me to turn this on and off. The existing Fortran code is much worse. So the other big difference is that Zephyr was built from the ground up with the idea of parallel in mind, and that's what I'm going to spend most of the rest of the time talking about. So I'll give you an example of what it looks like to run a forward modeling in Zephyr. This, by the way, is running in a Jupyter notebook. The server it's actually running on is at Western, and it's an Intel Xeon workstation with 96 gigs of RAM and 16 cores. So it's got a little bit of room to for us to stretch our legs. So Zephyr is separated into a front end and a back end and a middleware layer. And that middleware layer is actually where most of the SimPEG integration happens. And so the back end is really primitive things like the discretization. So I can say, I want to import a particular discretization and a particular way of generating a source right-hand side. And then I'll create a grid that is 200 cells high and 100 cells wide with a constant velocity and a constant density and square cells. And I'm going to model for a frequency of 100 hertz. So then I just set up this mini Zephyr instance with that. And I set up a source generating instance. And then I can say, OK, well, give me a right-hand side. And this right-hand side is a sparse matrix that contains just a few non-zero elements. And these have to do with a 9x9 region for each column that is used to interpolate for the source location. And so if we wanted to forward model that, we just multiply the system onto the right-hand side, and it doesn't take very long. And then we could plot the result. If we had a slightly more complicated velocity, so something like this here, let me see if I can plot that. Where we have a higher velocity anomaly in the middle, then we could forward model that, and we get waves that are propagating for a monofrequency oscillator through this medium, and then they get accelerated as they go through that section. And so the phase of the arrivals is advanced a bit there. But of course, that's not really all that interesting. But we can do the same thing in parallel. And this is where I think Zephyr has some advantages. So now we can say, I want to set up a very similar system, but instead of a frequency, we're going to specify frequencies. And this is 8 from 50 to 450 hertz. I'm going to say, here's the discretization that I want to use, which is the same as the one I used in the previous step, just now it's specified at one level of abstraction. And then I say, OK, well, actually, I'd like that to be parallel. So if I run this, now what I have is this system, and it has subproblems associated with it. And so each of those is an instance of the discretization that we looked at before. And I could grab one of those, for example. And see what its frequency is. And if I look at another one, we'll see that frequencies are just distributed over those. There's no magic happening here. All it's really doing is wrapping around the multiply and wrapping around the setup so that we have these multiple right-hand sides, or pardon me, multiple left-hand sides. We could also have multiple sources, same as what we had before. But now we multiply that combined system onto the right-hand side, and it does a little more work. There's a few workers that spin up on the right-hand side right here. But it didn't take a lot longer. And we could plot the results. And we can see here that what we get back is a generator, which we turn into a list over all of the frequencies that we worked on. And then each of those has something the same size as the right-hand side that contains the different sources. So we can see the first source for the 0th and 5th frequency. We can see the 4th frequency there. We can see the second source for the first frequency, etc. This is just returning a collection of results. And the real advantage is that if you think about the math of this, the multiplication for a fixed right-hand side for, in this case, 8 different left-hand sides is completely separable. This is what we call an embarrassingly parallel problem. And so what that means is that there's effectively zero effort. In practice, of course, there's some, but in terms of the mathematics, we can get an almost linear speed up in terms of taking this and making it parallel. So how exactly do we do this? Well, for a long time, Zephyr has used one of the built-in interfaces in Python called multiprocessing. And the goal of this is to try to map, well, so multiprocessing gives you some low-level options, but one of the most common ways of using it is to take a functional and map it over a sequence of inputs. And if you think about this, you know that in Python, when we define a functional, we say something like def f of x, right? And it does something. But in this case, in many Zephyr instances are just a class, and those classes have a call method on them. So it'll be a right. So that's how we would define a class that behaves like a function. And so it turns out that we can use we can do the multiplication the same way. And so the same pattern here where we're mapping a function onto a number of different right-hand sides is really, really easy with multiprocessing. Similarly, we could go through and we could create a subprocess which is somewhere down in here. Suffice to say that we can create a bunch of independent subprocesses and say, we'd like to apply a function to a right-hand side. And so then what we could do is go through there and say, actually, I'd like to apply 8 functions to this right-hand side, and then get the results for those. And so we look at how Zephyr does this. That's very much what it does. The multiprocessing distributor here implements a multiplication. And this multiplication has a bit of work to get the various right-hand sides and the various left-hand sides. And then it just says, I would like to apply that asynchronously for each left-hand side to each right-hand side. And then it goes through and it says, I'm going to make an iterator, which is a lazy evaluation object, to get all the results of those multiplications and then return them. And so they'll run in the background. So there's another system, and I think that if, from a point of view of implementing parallelism in SimPEG, this is actually the one that we want to be looking at. And it's called Dask. And some of you may have heard about this. I know a number of people in this call were at SciPy this year, and there was a great deal of discussion about Dask. And so Dask does a couple of things. It tries to take a bunch of pieces that go into an overarching computation and separate them on a directed acyclic graph. And all that means is that A depends on B, so B has to happen before A. And then C depends on A, so A and B both happen before C. And so it creates a graph of tasks, and then it runs them using a distributed scheduler. And so there is a subpackage called Dask distributed, and it does something very similar to multiprocessing. In fact, one of the options is under the hood that it's using multiprocessing. The advantage is that this is very, very scalable, and it's designed to be able to operate on a variety of different environments. And so we can see what that looks like. If we look at these two examples, this will give you an idea of the sort of thing that where we might benefit from this. So Zephyr is implementing this numerical solution of a wave equation. But of course, if we're only going to have a constant velocity medium, we know what the answer to that solution is, right? We can define an analytical solution. And so what I've done here is created an analytical Helmholtz function that behaves very much the same way. And then we give it a system config, and it can take this in and work with it the same way that Zephyr does. So we create a Zephyr instance and an analytical Helmholtz instance. And we say, please generate a wave field for the analytical case and the numerical case. And we can see that in the right-hand two images here, the analytical Helmholtz wave field is really pretty well approximated by the numerical version. The difference is there's some edges that are damped out because of perfectly matched layer boundary layer, and the source region isn't quite right, which has to do with just the way that we're injecting the source. But the fit is pretty good. So that's how we work with a 2D analytical Helmholtz system. But of course, we can also calculate an analytical response for a 3D system, right? But what if we only have a 2D system of equations on the numerical side? Well, it turns out that using a 2.5D approach, which means that we're taking a bunch of plane wave components and integrating them together to get the effective 3D response, we can do a pretty good job of approximating the 3D response just by combining a whole bunch of solutions of 2D problems. And so maybe we run that, and we only used 8 subproblems there. And then we compare the two, and we say, okay, well, that's all nice. But outside of a region very near to the source, the fit isn't very good between the now 3D analytical solution and the 2D one, right? Or the version, I should say, that's composed of 8 different responses from different 2D subproblems. So, let's say, well, 8 isn't enough. We want 16 of these. Now, if we were doing this in serial, that would take 8 times as long, times 2 is 16 times as long as computing just a single frequency, right? But because we're doing it in parallel on a machine with 16 cores, it takes the same amount of time, which is nice. And on the right-hand side, you may have seen I'm not sure how well it's coming through on the video, but each of those red lines represents a Python worker that starts up, runs for a bit, and then stops and returns a result. And so there are actually 17 of those. There are the 16 that computed the answers, and then there's one that's running the notebook that combines the results. But we say, okay, well, the error here is actually still pretty high. It doesn't look too bad if we take a cross section, but if we plot the relative error, it's like really bad. So maybe we want to do 32 components. And that didn't take that much longer, and it's starting to get better. Maybe we want to go to 64. And this takes a little bit longer because we've started to hit the point where we're actually doing serial computations. But we're getting a much better approximation to the analytical system. And of course, approximating an analytical system is not really that interesting. But as an example of the sort of way that we want to operate, the thing is that when you work in these big problems and you have a whole lot of different right-hand sides or left-hand sides, the problems get big very, very quickly. And so we say, okay, well, maybe that's not quite right. What if we want, 1,024 components? Well, that's going to take a little bit longer. But if we write things correctly, it works just fine. And so what happens is we have a whole bunch of, I think actually 32 threads that are running on the right-hand side. They're all at about 100% CPU usage. And every once in a while, they die off as they finish a task. And the result gets spun up and integrated on the one of the main Python workers. And so if you think about it, if we have 32 workers and 1,024 tasks, it needs to go through this process 32 times to solve the problem. If we weren't in parallel, then it would take 32 times as long. And it's already taking a couple of minutes. So that's really not what we want. But by parallelizing, we can get a lot of benefit. And the point here is that we can parallelize over not only something like plane wave components, which are multiple left-hand sides. We can parallelize over frequencies, as we saw in the example that I showed you earlier. And we can parallelize over right-hand sides. So we can say, okay, we've got a whole bunch of sources. And the strength here is really, when computing multiple sources is expensive. We can get a whole bunch of sources, and we can compute those in parallel, too. And so the advantage of something like Dask is that it lets us not have to worry about some of these problems. and they just work. And I'm running this on my laptop at home, but it's actually running on a big machine at work. You know, the interface doesn't have to change between doing back of the envelope calculations and doing real problems. So that finished, by the way. It takes a little bit longer, but it's not that big a deal. It's about trying to take these big problems and democratize the solutions of them. And so by abstracting away a lot of the complexity, we can do that. Something a little bit more real, maybe. Here's an example.
Yeah. So
yeah,
everything is running on the clusters, but your notebook is actually on your laptop. And like how? So where is it leaves? Like, so you have some images that you get back or arrays. You can actually type whatever array you have, and then you can probably, like, I don't know, save it or something like that. But so what leaves, like where it leaves, it looks like a magic, but where actually those kind of things happening and like.
Right. Here, let me maybe take some of the mystery away here.
I think the Jupyter is still also on the remote server.
That's exactly right. Yeah, Jupyter is also running on that server. There are ways to do that. So if you guys have tried to do pre-reading that I didn't send any information about, you may have noticed that there are 2 Zephyr projects. There's the one on the UWO-SISE, which is the Western Seismic Imaging and Inversion group on organization on GitHub. And this is the code that I'm actually showing you today. If you go to my personal GitHub, there's one from, like, I don't know, 2 years ago now with the same name. And I basically did an out-of-tree rewrite of this under the other organization when I realized that the stuff I was working on was not actually that good. But this made heavy use of something called what is it? IPy parallel, IPython. This way of using parallel compute clusters in IPython directly, which is now Jupyter. And so what this does is lets you have like a star topology. So instead of having a whole bunch of peer workers, have a whole bunch of workers that connect to a central, to your, say, kernel on your notebook. And then you can farm out work to those, and then they could maybe talk to each other with MPI. And so if you're interested, you can see what that looks like on this old Zephyr repository. That's not actually, and so what I did is wrote a batch scheduler and so on. It really was not the right way to do this, and that's why I've stopped working with this and gone for a more shared memory approach. But that's definitely one thing you can do. In the case of what I'm showing you today, it looks here like I'm connected to localhost, but what I'm actually doing is using a trick. So if I stop this, when I logged into that server, I told it to forward port 8888 from localhost on my laptop to localhost on the remote server. So I can start the notebook over there, and then I can port forward here, and then connect to localhost. But that's actually running on a server a 2-hour drive away. And of course, now all my notebooks are angry with me. But the point is, it works. And so if I do and top, I can start hitting letters. Get this just the way we want. Sort by memory, and then say, I don't know, like only show Python, and then change the update to every like 100 times a second. And so that gets us roughly back to where we were. So if I were to, for example, run a seismic wave field simulation here, we would see the Python kernel start up on the remote server. And you can see when when this goes red, that's actually the server starting up. Interestingly, I added this bit today. This turns off the Dask parallelism and switches back to multiprocessing because I've discovered there are certain of these demos where the Dask parallelism isn't quite working properly. And so we can run this and we say, okay, you know, maybe I want like 16 workers, and I'm going to load my configuration from a pickle file and then do some forward modeling on 16 workers. And eventually I'm going to do some kind of a Fourier transform to generate time domain data. And this is the example that I used when making animations for the SciPy conference. You can also see here I'm using Dave Marchant's wrapper PyMKL that wraps around the math kernel library that's included with newer Anaconda distributions. And so each of these workers is spiking around like 400% CPU because they're threading the PDE solves as well. So that finishes, and then we get the main worker process is running for a while, mostly just generating PNG images because I have these fairly high resolution images that I'm creating here and creating frames of a video. But at that point, there's really nothing parallel going on. It's just a normal Python notebook. And so we can see what wave propagation would look like from a whole bunch of different frequencies. And this is in the diamond example that the SimPEG group showed at SciPy. So this, of course, is a heterogeneous model, and the actual velocity model that's being shown here is not included in that image just for brevity's sake. But if we plotted it, it's upside down, but it looks roughly like that. Yeah, so no magic. It's just kind of SSH tunneling trickery. So that's mostly all. That's what I had. I just wanted to show some demos and say, here are some of the things that you can do. The big difference between Zephyr and SimPEG is that Zephyr was, to some extent, written with parallel in mind. And I mean, the other thing is, to go back to the Fortran C, can Python really handle the performance question? We have this Fortran code. It's 25, 30,000 lines of Fortran with 30 years of development. And for those of you who saw my talk at SciPy, you know that I have a way of taking the Zephyr solver and embedding it in that Fortran code. It's about 3 or 4 times faster than the pure Fortran code. And that's not magic. That has to do with the fact that MKL Paradiso is very, very highly optimized by people who are computer scientists and know how to solve numerical systems very, very quickly. And the solver in the Fortran code was written by a PhD student in geophysics 20 years ago. There's no magic. It's just that we're able to actually take advantage of 20 years of research by people who actually do this for a living. It's nice.
So Brendan, are you planning making some sort of general structure that we can use? Because I know it's a pretty specific kind of structure that goes for Zephyr. But
so
Python for parallelization at the moment. But what do you think? Our current problems, it's a big hurdle that we can sort of make that as a parallelization.
I think it's possible, yeah. So this is scrolling through a whole bunch of tiny text is maybe not what we want to spend the time on here, but you guys can of course have a look at the source code. This is all on GitHub, but Zephyr. This is Mini Zephyr, which is a really bad name for the main discretization that's inside Zephyr. And what it does is it uses a problem or a project. I call it galoshes. I think there was some metaphor there that made sense at the time. And it does a very basic sort of like a properties or traitlets like mapping of various inputs to properties on a class. And so it has this kind of interesting inheritance, but suffice to say that we're defining what inputs we want. And then right at the end, we say, you know, by the way, if you multiply this by something, apparently we don't actually say it here, somewhere in, I'm going to say discretization.py, which that other one inherits from. Somewhere we have this mul, right? And all it does is it says, you know, I want to take a sparse, it's actually a solver representation of the inverse of my matrix and multiply it on some kind of a right-hand side, and then maybe my sign convention is totally wrong, and so we're just going to conjugate that. It's hiding all manner of sins there, but and then calling this is like it's just the same thing. So then we have this discretization wrapper, and what it does is it defines that there are these sub-problem configurations, and so all it does is it takes the dictionary that it's initialized with, and like it makes a copy of it, and then adds the subproblem configuration to that and overrides certain things, and strips out certain keys that would be included if we were running this in a non-parallel environment. And so then the multiplication here, it says, well, it's not implemented. And the reason that it's not implemented is because there's this whole structure of distributors that do these things in various ways. So it's composable, but there's no reason that SimPEG can't do something similar. All you have to do is define an object that looks like a problem, but in practice it is abstracting over multiple problems. So here's the multiprocessing distributor. It has a bunch of properties that say things like, you know, this is the number of workers that I have, but the multiplication is not actually that complicated if you hide the fact that this is, most of this code is about saying, you know, do I have one right-hand side or do I have a list? You know, it says if it's parallel, submit a task to the task queue, multiplying the left-hand side by the right-hand side, and then add that to a list, and then loop over the list and get the asynchronous results in some way that's sort of efficient, and then pass this back to something upstream. And if it's not parallel, then just do the same thing, but don't do any of the asynchronous task queue, just return the result directly. So this is where the SimPEG integration gets really weird, because this is dependent on a version of SimPEG from last April. But Zephyr actually has a survey and a problem. And so like if I go to this one and we say we want to compute a gradient, we can have a system config. And then we have a problem and we have a survey and we pair them. And then we say dobs is survey.dpred. We set a survey as observed data, standard deviation, data misfit. You know, we compute a residual, and somewhere over here, this thing is going crazy. And then we can eventually compute a gradient and so on. So all that's doing is going into problem.py here. And the base problem takes one of these system config objects that I've standardized on. And then it has, you know, JVec, and it has JTVec. And so if you want to see what the Jacobian does, it has a whole bunch of things that may be optional because they may already be computed, which is sort of breaking the way that SimPEG works. And then what we do is we say we get a whole bunch of right-hand sides. If they're iterable, then we stack them in a special way, and if they're not, then we don't. We can take both the real right-hand sides and the back propagation virtual sources, right? The left-hand or the right-hand sides for the back propagation system, which is done with the same matrix factors. And then we say this terrifying thing, which says we're going to add together the results of the multiplexed combination of both the forward right-hand sides and the back propagation right-hand sides for every frequency in the list of frequencies. And then the gradient is eventually just reducing over those results. So the point is that this is implementing a Jacobian that's sitting on top of that. And what it's doing is relying on the fact that these things that look like they're just a system that multiplies by a right-hand side actually do the parallelism under the hood. And then there's a lot of work here to allow for the fact that we don't actually want to form these things in memory before we pass them back to the thing that extracts the data. So then you get to the survey, and it has a way of pulling the data out of this that projects fields, but it has a lazy version of that takes that iterator that we generated in the problem, and it loops over the results of that iterator on the fly. And so each time one of those things is finished, it takes the result, pulls it off of the iterator, projects out the fields, and then throws away that wave field, so that it's never actually storing more than like 2 times excuse me, 2 times the simultaneous number of frequencies times the number of sources wave fields. So that's how the parallelism works at like the Jacobian level. So how would we do that in SimPEG? Well, if you're parallelizing over frequencies, it's actually really easy. You just say, now we have a problem that takes a list of frequencies instead of a single frequency. And then when you have a right-hand side, maybe it takes a list of right-hand sides to have different source terms. And then it just goes through and it says this one multiplies by this one multiplies by this, so on. And it doesn't have to worry about the details. It says, Dask, go do this for me, or multiprocessing, go do this for me. The details matter to get performance, but to some extent, that's something you can solve once. It gets more.
Are you using so? Because I think you're using multi-threading for multiprocessing, so it's actually the shared memory. So in that sense, you don't need to pass that many things, am I right? Or because it shares the memory, so it knows everything.
Yeah, so the details of that are a bit complicated, and it depends on how much abstraction you want. Dask will allow you to do distributed computation as well, in which case it's not shared memory. And so if you program in a way that assumes that it's distributed memory, one of the advantages of Dask is that it will you'll still get the performance benefits of not copying that data if you're on the same system. But then all of a sudden, when you are on a different system, what it'll do is it'll pickle up those inputs and send them across the network to the other system and unpack them. So I would say there are a lot of benefits to not assuming that you can do shared memory. But in practice, yeah, you probably can. And the nice thing is that if you have a framework like Dask that is aware of that, it will to some extent handle it for you. Multiprocessing, on the other hand, unless you are working with very specific types of structures like memory mapped arrays, it will actually pickle up your data before it sends it to the workers, and then pickle up the result and then return that. And that's a big memory hit when you're on the same system, which is not ideal. The other thing to think about would be in some of these wrappers around things like Pardiso, and it's possible Dave is already doing this, or that Rowan's doing this in PyMat Solver, is to release the GIL first, which is the Python Global Interpreter lock, before it goes out to the C or C++ code that it's actually calling when it calls Pardiso. And I suspect that if that's not already being done, if we did that, then you could use the thread executor in Dask, which uses multi-threading instead of multiprocessing. And the threads shouldn't block each other if you release the GIL. Mm. The details of that are tricky to do, and I haven't tried it, but that might cut out a lot of the overhead of creating multiple processes each time. And you could see that in all those cases, it was spinning up like 32 Python interpreters that were forked from those other processes. And the other thing is that starts to matter a lot when you're on Windows, which doesn't have a fork call, which means that some of the assumptions that we make in the Linux, Mac OS, Unix world aren't necessarily true on Windows, like that you can copy that memory for free, or rather avoid copying that memory because the child processes can access it directly. So, but yeah, the problem of exactly how to make a parallel problem, like a SimPEG problem, it turns out kind of complicated. I spent a while on it. And the funny thing is that our grad students at Western are actually using this mostly through the Fortran code integration. And it's letting them work on things like Sean Haddon, who's actually on SimPEG Slack now, he wrote rather than just a viscoacoustic Helmholtz solver, he wrote one that does viscoacoustic anisotropy, which is non-physical but useful. It'll let you do a good approximation to tilted anisotropy. And so the only differences between that and Mini Zephyr are, where are my notes? Yeah, so this is called Urus, and like that's the full source code. So what he's got are all the discretization terms here, and it's complex because it's using a 9x9 per axially rotated multi-grid thing with optimal dispersion characteristics and PML boundary conditions and so on. But like he spent all of his time writing that, and the stuff that I did to make the Mini Zephyr one parallel, he just gets kind of automatically, and it works fine. It takes it's about 4 times slower than the and uses about 4 times as much memory because it's a vector system, but and it has to take in the anisotropy parameters as additional inputs. But other than that, the use is the same. And yeah, so then he's benefiting from the integration that I have with our Fortran code, and that our Fortran code, which is 30 years old now, all of a sudden supports parallelized vector systems in anisotropy, which nobody wanted to write in Fortran.
That's very cool, Brendan. Do you, for your links that you showed us, are those available like on your GitHub, or can we access those examples easily?
Yeah, that should be doable. I made a bunch of tweaks this morning to those examples to get them to work with the current version, and so I will maybe just commit those and put them on a branch.
Sure.
And I will send the link maybe to you, Lindsay, and then is that the easiest? And then you can distribute it, or I can put it on Slack.
Yeah, either to me or Slack or both.
Or both. Yeah.
That would
sure,
be
I will do that. Yeah, and those links are just in a notebook, so I can I'll just commit that along with it. Okay. So it'll be in well, I'll put the information in Slack, but I'll probably just link directly to that notebook on GitHub, and then you can go from there.
That would be great. Cool. And then I guess for sort of closing comments, for us getting started with implementing Parallel, what would your main pointers be? And do you have like a favorite tutorial that you started from, or anything there?
That's changed a bit over the years. I think I would say there are a few things to look at, and I don't necessarily know for sure what will work best for the bulk of the SimPEG community. I think Dask is what I would recommend looking at now.
Okay.
It's not so much a favorite as it is, I think, the right way to do it. In that I actually have not explored it as much as I would like to. But what it does is it gives you a very high-level interface. It gives you access to the performance benefits of some of the low-level things by kind of multiplexing over them. So it says, okay, let's pick the best way to do this based on the configuration you've given me. And it allows you to avoid having to think about some of those pieces, which is nice. under the hood, it's going to be using multiprocessing, Python 3's concurrent futures module, or Python threading, native threading, or potentially it's going to make use of some of the distributed communications toolkits. And I think that there are like half dozen that it supports. The other thing you could look at, it's a bit of a can of worms, but it could be useful for some of these problems where the pieces need to talk to each other, is you can actually do MPI in Python, no problem. There's MPI for Pi, and it's a fairly thin wrapper around the Python, or around the MPI-C API. And so you can do message passing back and forth, and what it has are two levels, a high level and a low level interface. The low level interface, you give it NumPy arrays, and it passes them through memory sharing the way that C does. It's very efficient. The high level interface, you give it Python objects, and it pickles them and then sends them over the network and then unpickles them, which is much slower, uses a lot more memory, but is really easy to use.
Yeah.
So I think I would probably say, I would start with Dask.
Okay.
If there's a case where you need to run jobs that talk to each other, like you're doing time domain and you need to synchronize the edges of a grid or something, that's where the MPI case might make sense.
Yeah.
Multiprocessing is great, but unless you're using it correctly, you can have a lot of overhead from copying memory. Threading is great, but unless you're using it correctly, you can run into problems actually getting compute parallelism in Python because of the global interpreter lock.
Yeah.
And for just pure, this is fun and it's easy and you can do it in like 5 lines of code, maybe look at concurrent.futures, which is available in Python 3 and backported to Python 2. And it lets you just say, go do this somewhere else and then ask for the result later. So it's a really, really easy way to do, backgrounding of tasks and things like that. And it can do basic parallelism itself.
And with Dask, we should be on Python 3. Is that best?
I think it fully supports both.
Okay.
But my general rule of thumb these days is if you can be on Python 3, why would you use Python 2?
That's fair.
I think Python 3 is better. It's a lot easier to write code with fewer bugs. And I mean, Python 2 support is going away soon.
Yeah.
If you start a PhD now, Python 2 will probably break on you between now and when you finish. So, Python 3 is the obvious choice if you can. If you can't, I think Dask is fine too.
Okay. Yeah, that's a good point. Most of us, I think, are still on Python 2 just out of force of habit, more than anything else. But I think, getting motivated to switch is a good thing.
I will say Zephyr doesn't actually run in 3, so I get that.
Yeah.
It's not that it's banned, it's that I haven't, as some of you guys know, I'm not actually a full-time academic anymore. I'm an adjunct at Western, but I work for 3 Point Science full-time. And some of the maintenance of this needs a little bit of care that I need to come back to.
Cool.
But yeah, I think Python 3 is, if you can use it, I think it's better, personal opinion. But I would recommend that.
That sounds good. Does anybody else have questions or things you want to ask Brendan while we've got him? And too, like Joe, Andrew, and Dom, feel free to chime in.
That's good. I think I'm kind of convinced it's the way to go. And thank you, Brendan.
Yeah,
No
thanks, Brendan, man. You're a few miles ahead of me, so eventually I'll get there.
Yeah, but at the same time, I'm really looking forward to seeing what can be done with SimPEG in this, because the code that I showed there is very, very close to the discretization. And I think that being able to take some of these things and leverage that with SimPEG to get the speed up, but also symbolic nature is really, these days I am a computer scientist, even though it's not what my education is. And if you guys can help people not become computer scientists when they want to do geophysics, that's
and speed up is always good.
Yeah.
Thanks again.
Yeah, no worries.
Perfect. Well, thanks for your time, Brendan. Much appreciated. And I think that this is this is exciting. This gives us a lot to start with and play around with, think about, and hopefully we can sort of start putting a push on maybe just for even starting with frequency domain codes and some of the simpler cases and go from there. So
I think frequency domain, I mean, not trivial, but the problems are inherently separable.
Yeah.
So that's an easy step. Time domain's a little harder because you've got to synchronize boundaries, potentially.
Yeah.
So.
Perfect. Well, thanks. We will see you guys later, and we'll be in touch on Slack. And I will post, Brendan, once you send me the links, I'll post them sort of with this video so that we have everything in one place. So
Perfect.
Sounds good. Thanks, guys.
Bye, everyone. Bye-bye.
Yeah.